You know, there's something really captivating about numbers, isn't there?
Definitely. They seem so structured, but then they have these little quirks.
Exactly, like a little puzzles hidden inside. And today, we're diving into one of those quirks. A really peculiar behavior found by the Indian mathematician Dr. Kaprekar.
Yeah, yes, Kaprekar, a fascinating figure.
We're going to explore what people call Kaprekar's constant, mostly the four-digit one, 6174.
That's the most famous one,
But
yeah.
we'll also touch on, similar things for other numbers of digits, different dead ends, basically, and even other number systems.
It gets quite deep.
And your sources mentioned this was back in 1949, right? And apparently people were a bit skeptical at first.
Oh, very much so. It took a while for it to be fully appreciated.
Okay, so let's dig in. The main event, Kaprekar's constant, 4 digits. How does this actually work?
Well, it's actually quite elegant in its simplicity. You start with any four-digit number.
Any number.
Well, almost. The only rule is that not all the digits can be the same. So not 1111 or 2222, that kind of thing.
Got it. So like 1234 would work.
Perfect example. So you
Right.
make 1234 first step.
Yeah.
Arrange those digits to make the biggest number possible.
Okay, so 4321, 4321,
Exactly. Then you arrange them to make the smallest number.
which would be 1, 2, 3, 4, 1 through 3 to 4.
Right. Now you subtract the smaller number from the bigger number.
So 4331 minus 1234. Okay, let's see. 3087.
You got it. 3087. Now here's the core idea. You take that number, 3087, and you do the exact same thing again.
Okay, so digits are 3087. Biggest number is 8730.
Yep.
Smallest. Gotta remember the 0. And 378, so 378.
Correct. So 8 is 730 minus 0378.
Right, which gives 83734.
Precisely. And we repeat again with 8 of 352.
Okay, biggest is 8532. Smallest is 2358. Subtract.
You get
So-
6174.
There it is. Digits are 6174. Descending order is 7641.
Right.
Ascending order is 1467.
Okay.
Subtract 1467 from 7641, and you get...
6174. It just
Cheers.
loops back onto itself.
Yeah.
Exactly. It's a fixed point, a dead end, as you called it. Once you hit it, you stay there.
That's amazing. And your sources mentioned something about how quickly this happens.
Yes. Nishiyama did a computer study, found it takes a maximum of just 7 steps.
7 steps. That's it. From any valid 4-digit starting number.
7 steps or fewer, you'll always land on 6174.
That's... wow. Pretty wild. And there was something else in the notes about divisibility by 9 and 3.
Ah, yes, that's another fascinating layer. Every result you get from the subtraction step.
Like the 3087, the A352.
Exactly. They're always divisible by 9.
Yeah.
And therefore also by 3.
Why is that? Is it just coincidence?
Not at all. It's a fundamental property of our base 10 system. When you rearrange the digits of any number and subtract the rearranged number from the original or vice versa, the result is always a multiple of 9. Always. Think about place value. When you rearrange digits, you're essentially swapping place values, and the differences are always multiples of 9. Since the Kaprekar process is subtracting rearranged versions, each step has to give a multiple of 9.
Okay, that makes sense. Like a hidden rule. Now, you mentioned earlier that Kaprekar faced some skepticism.
He did, yes.
Okay.
According to your sources, some mathematicians at the time thought it was a bit, well, childish. Not serious mathematics.
Really? That seems harsh for discovering such a consistent pattern.
It can happen with novel ideas, even in math. But eventually, Martin Gardner wrote about it.
In Scientific American.
That's the one. That really brought it to a wider audience, and people started appreciating the ingenuity of it. He got his recognition in the end.
Good. A story of persistence, then. Okay, so that covers 4 digits, but the material said there are similar things for other digit counts. Let's try 2 digits.
Right. Same process, but with 2 non-repeating digits.
So like 30.
Okay, start with 30. Descending is 30, ascending is 03. Subtract.
30 minus 3 is 27.
Now repeat with 27.
Descending 72, ascending 27. 72 minus 27 is 45.
Again.
45. Descending 54, ascending 45. 54 minus 45 is 9.
And what if you try with 9? Descending is 9, ascending is, well, 0.9 minus 0 is 9.
So 9 is the dead end for 2 digits.
It seems so.
Yeah.
Your sources give other examples like starting with 23 goes straight to 9, or 48 goes 36, 27, 45, then 9.
Interesting. And I bet the results 27, 45, 36, they're all divisible by 9 too.
Spot on. That property holds.
Okay, how about 3 digits, another constant?
Yes, indeed. Same process again. 3 distinct digits.
Let's try 7, 8, 10.
Okay. 710 descending is 710. Ascending is 017. Subtract.
7 and 10 minus 17 is 693.
Repeat with 693 descending 963, ascending 369.
963 minus 369, 594.
Now try repeating with 495.
Okay, 954 minus 459 is, 495 again.
There's your three-digit constant, 495.
And the example shows starting with 123 also gets you there, just takes a few more steps.
Right. And 963 gets there pretty quickly, too.
And let me guess, all the results, 693, 594, divisible by 9.
Absolutely. And notice 495 itself. 4 plus 9 plus 5 is 18.
And 1 plus 8 is 9. So yeah, divisible by 9. That pattern is really strong.
It is.
Okay, so we have constants for 2, 3, and 4 digits. What about bigger numbers? 5, 6, up to 9 digits.
This is where things get a bit different. For 5 to 9 digits, generally you don't get a single constant like 6174 or 495 if you stick to the rule of no repeated digits.
Why not? What happens?
Well, the process often breaks down because the result of the subtraction ends up having repeated digits.
Oh, I see. And the process relies on rearranging distinct digits each time.
Exactly. If you get a repeated digit in your result, you can't strictly continue the same way, generating a unique largest and smallest number without repetition.
Can you give an example from the sources?
Sure. Take 5 digits like 1, 2, 3, 4, 5. First step. 5, 4, 3, 2, 1 minus 1, 2, 3, 4, 5 is 41976. All distinct.
Okay.
Now repeat with 41976. Largest is 97641. Smallest is 14679. Subtract, and you get 82962.
Two twos. Repeated digit.
Exactly. So the standard process kind of stalls there. Your sources show similar things happening for other starting numbers, and for 6, 7, 8, 9 digits, you often hit results with repeated digits fairly quickly.
Like 12346 gives 51975, repeated 5s. Or 123458 for 6 digits gives 730863, repeated 3s.
Oh, precisely.
But wait, even though there's no single constant, are those initial subtraction results still divisible by 9?
Yes, they are. That divisibility by 9 property still holds for the subtraction step itself. It's just that the iteration towards a single constant gets blocked by the repeated digits.
So no neat dead ends for those middle sizes, but what about 10 digits? That seems like it should be complex.
You'd think so, but 10 digits using all digits 0 through 9 exactly once actually yield a constant again.
Really? How does that work?
Well, the largest number you can make is 976543210.
Okay.
The smallest is 0123456789.
All right.
Subtract the small one from the big one.
98765432110 minus 0123456789 gives 975308641.
Now, what happens if you apply the process to that number? Arrange its digits descending and ascending.
Wait, the digits are 975308641. The descending order is 98765432110. Ascending is 0123456789. Oh, wait. The digits of the result, 97530866421, are different. Let me rearrange those. Okay, descending, 977654321. No, that's wrong. Descending of 97530866421 is 97530866421. Descending, 987654321. Ascending, 0123456789. No, I am rearranging the digits of 97530866421. Largest number for those digits is 976543210. Smallest is 01234678. Oh, wait, one careful. Let's use the results digits 97530032110. The largest number you can form using these 10 distinct digits is 987654320. The largest number you can form using these 10 distinct digits is 97765432110. Smallest is 123456789. Note there's let's use 1 2 3 4 5 4 3 1. Digits 9876542.1. Digits 995543221. Digits 987644321. No, those are not the digits. The digits are 97530866421. Digits 9876432. No, those are not the digits. The digits are 975308642.
My apologies, let's clarify. Start with 09. Largest, 98765432110. Smallest, 0123456789. Subtract, 98765432110. 0123456789. -853086421. Okay, that number, 97530866789.
Right. 987-654-3210 minus 123456521. Let's rearrange its digits. The digits are 9753086421.
Okay, so largest from those digits is 987-654-3210. Smallest is 01234567889. No, it has to use those specific digits. Smallest is 103456789. No, 01234567889. Wait, 01234567889. Wait, no, 753086421. All digits 0-9 are there. Sorry, I was confused.
Well, it's a big number. So the digits are indeed 0 through 9, just scrambled in 997-530-86421. So if you rearrange those digits to be descending, you get 987-654-3210 again.
Right.
And ascending, you get 013346789 again.
And the subtraction is 975308641 again.
Exactly. So 97530866421 is the constant for 10 digits. It's reached in just one step and stays there. Wow. After the complexity or lack of a constant for 9 digits, 10 digits just snaps right back to a constant. And divisibility by 9.
So told, the sum of digits 0 through 9 is 45.
4 plus 5 is 9, so any arrangement and the difference must be divisible by 9.
Correct.
Okay, this is fascinating. Your notes even mentioned exploring this in other number systems, like not base 10.
Yeah, the principle can be adapted. The sources mention octal, base 8, and hexadecimal, base 16, briefly.
What?
But let's look at binary, base 2. It's simpler, but illustrates the point.
Okay, binary, just zeros and ones. So the only distinct digits are 0 and 1.
Right. So the descending order number you can make is 10.
Which is 2 in decimal.
And the ascending order is 0, 1.
Which is 1 in decimal.
Now subtract in binary. 10 minus 0, 1 equals 0, 1.
So 1 in decimal. And if you repeat with 0, 1 or 1 decimal, descending is 1, ascending is 0, 1 minus 0 is 1.
So 0, 1 or just 1 is the dead end in binary.
Huh. Simple, but it works the same way. Your notes add that 0, 1 is the 1's complement of 10.
Yes, sort of the opposite in that simple binary context. And 1 is divisible by 1, which is base 1 for binary, similar to 9 being base 1 for decimal.
So that divisibility pattern seems key across bases, maybe linked to base 1.
It seems to be. That property, the difference between rearrangements being divisible by base 1, is quite fundamental.
Right, so recapping the main ones in base 10. 9 for 2 digits, 495 for 3, 6174 for 4, and this huge 97530866421 for 10 digits, plus 1 in binary.
Those are the key attractors we found.
It really is amazing that this simple process, arrange, subtract, repeat, just pulls you towards these specific numbers, like mathematical gravity.
It is quite remarkable. It shows an underlying order where you might not expect it. Kaprekars' work wasn't just a party trick. It pointed to, deeper structures.
And your sources hinted this might even be useful, maybe in computer algorithms or something.
It's a possibility. Understanding these kinds of stable states or predictable outcomes in numerical processes, well, it could potentially inform algorithm design or maybe data analysis techniques. You never know where these theoretical curiosities might lead.
It's a great reminder of that connection. So, wrapping up this deep dive into Kaprekars' world, it kind of leaves you wondering, doesn't it?
How so?
Well, if you can find these predictable dead ends, these attractors, in a system as seemingly straightforward as numbers, could similar stable states exist in other systems that seem much more chaotic?
Like in nature, or social systems, or even technology networks.
Exactly. Are there hidden Kaprekar constants, metaphorical ones maybe, lurking in other complex systems, just waiting to be discovered? Something to chew on, anyway.
Definitely food for thought.